Hi. Hi. We are Team 25. My name is Ricardo Charlestin. My partner is Xavier Bercy and Brian Murton. We worked on a project that consists of two parts. Part one, which is the Fourbar mechanism analysis and animation, and the second part will be the synthesis of slider crank mechanism. Just a little brief introduction. Mechanism was introduced in the late 1900s by a digital computer developer named Ferdinand Friedenstein. Our main objective for the Fourbar mechanism, which is the first part of the project, is to analyze the Fourbar mechanism with the dimensions and constraints given to us, then calculate the trajectory of points S for closure 1. We will later calculate the unknown velocities and acceleration of each joint, and then plot them as a function of the input. Then we will demonstrate a realistic application and create an animation of the mechanism motion. In the mechanics of a Fourbar mechanism, we have a rules called the Grashof rules, where the short length added to the longest length should be smaller to the additional length, and from the result you get, that will determine if you have a crank mechanism, a double crank mechanism, or a double rocker mechanism.
My name is Brian Murton. I did the calculations for this project, and I'm going to talk to you about the first part, which is the Fourbar mechanism. We were given link links R2, R3, and also the angles theta 1, and the coupler links were given. We chose R1 to be 45 centimeters and R4 to be 60 centimeters. What this did when we put it into Grashof's rule is it satisfied the inequality, which means it's type 1 mechanism, and because R2 is the shortest link length and it's attached to the constraint joint, it makes it a crank rocker. QS was given to us as R3, which is equal to 50 centimeters. It was also given at an angle of 35 degrees. So I'm going to turn off the lights now to make it a little easier to see these graphs. I used Excel to do most of the calculations. Excel is a great program because it works with a lot of numbers real fast. You just have to plug in one equation. One thing I learned is that it doesn't work with degrees, so you have to change everything to radians. So at first, I wanted to do a position analysis. Because theta 1 is given, sine and cosine of theta 1 are constants. Theta 2, it changes obviously from 0 to 360 degrees. I converted that to radians and then got the sine and cosine of theta 2. Using the equations from class, I found position x of point S and position y of point S. And up here, you can see that's the position analysis of the point on top of the coupler link. When you're doing a quadratic equation, you get two answers. So this is the first set of answers for that possible. And then when you're calculating the velocities, the relative velocities of the links, usually matrix form is the easiest when you're just trying to figure out one or two unknowns. But because I'm trying to do it for 360 different degree points, what I did is I just put in a very complicated equation, went all the way through for the first cell, and then copied it all the way down. Right at about 350 degrees, it's right where it's changing that very unstable point for the mechanism. This is what I was talking about earlier, about how you get two answers for a quadratic equation. That's the second set of answers. It's slightly different. It rotates the opposite way. This over here is omega 4 versus theta 2. Very similar to omega 3. It's a little bit less overall. It still has that same spike near the end. Up here, this is alpha 3 versus theta 2. It's slightly difficult to see. For the alphas, I did basically the same equations as the velocities. It was just a little bit more complicated, a little bit broader, but it was the same process. And this is finally alpha 4 versus theta 2. So you can see as it's changing, the coupler link, as it's moving from positive to negative, there's a big spike in acceleration. That's the point where on velocity, it's going from positive to negative and back positive. The accelerations peak at those points.
Hi, my name is Xavier Bercy, and I'm going to be talking about the crank mechanism animation. Basically, on the left-hand side, we have the crank mechanism animation of our project that I designed. And on the right-hand side, we have a screenshot picture of the Fourbar mechanism. Next, we have the realistic application. This is the door frame of the four-door mechanism. Then for our conclusion, we came up that the four mechanism is a type 1 crank walker, and we use the Excel sheet to find our solution, the manual calculation, and we demonstrate an animation for our project.
Hi again, this is the second part of our project, which is a slider crank mechanism. The slider crank mechanism is a type of mechanism that transforms linear motion to rotary motion. Our objective is to find a slider crank that will go to the given positions, to verify the design by kinematic analysis, and then animate the motion of the synthesis mechanism in a realistic world. Here are the given positions in inches that will make sure that the synthesis of the slider crank, if the AB on the coupler is required to take. Here's a table that we made throughout Excel. We used the given points, but we didn't really have to fix any of the points, which was one of the options that was given. We only decreased, we did an increment of decrement of 1 only in A1, in A3, I'm sorry, and then we were able to find the points 0.12, 0.13, and 0.23 as well. After all that, we were able to find GX, GY, and GX, which are coordinates that will give us the most important thing that we're looking for, which is theta. Here is a picture of our slider crank that will be in SolidWorks. And here's a realistic application of a slider crank, which is a standby engine. Utilizes a valve system, which is integrated into a crankshaft. It is not one of the most simple ones, but it is a slider crank mechanism. In conclusion, with the position equations, we were able to solve and make sure that the mechanism passes through all the required position that was given to us. That's the end of our presentation. Thank you for watching.